CUDA Programming Basics Part 2, Kernels. In Part 1 of CUDA Programming Basics, we discussed device memory allocation and how to move data between host and device. All of this memory management is performed from host code. In Part 2, we focus on code that runs on the GPU. We discuss kernel launches and specifics of writing GPU code. Kernels, or functions launched from the host and run on the device, are basically C functions, with some added restrictions. Kernels cannot access host memory and must have a void return type. Kernels also cannot be called with a variable number of arguments, cannot be recursive, and cannot contain static variables. Kernel function arguments are automatically passed to the device and do not need to be transferred using CUDA memcopy. If kernel arguments are pointers, then the value of the pointers are automatically passed, but the memory they point to is not copied. For example, if an array in host memory is to be used by a kernel, first the array is copied to device memory through CUDA memcopy, and then a pointer to the array in device memory can be automatically passed as a kernel argument. Because CUDA is a heterogeneous programming environment where both host and device code can reside in the same file, other function qualifiers are device and host. Functions with the device qualifier are both called from and executed on the device. They cannot be called from the host. These are typically kernel helper functions. The host qualifier denotes functions that are called by and run on the host, which is the default behavior. The host qualifier can be combined with the device qualifier to generate both CPU and GPU code for a function. Kernels, or functions declared with the global qualifier, are called from the host using a modified C function called syntax. This syntax modification is an execution configuration delimited by triple angle brackets and placed between the function name and function arguments. The basic execution configuration defines the dimensions of the grid and blocks that are used to execute the function. Both of these execution configuration arguments are of CUDA's built-in vector type dim3. The grid dimension in blocks is at most two-dimensional, and the sizes in each dimension are specified in the X and Y fields of the first execution configuration argument. The arrangement of threads within a block can be 1, 2, or 3-dimensional, and the sizes in each dimension are specified in the X, Y, and Z fields of the second execution configuration argument. Multi-dimensional grids and blocks are for the convenience of the programmer when dealing with inherently multi-dimensional data. All unspecified dim3 fields are initialized to 1. Several examples of specifying execution configuration parameters and launching kernels are given on this slide. In the first code segment, the variables grid and block are defined and are assigned values used to launch a two-dimensional grid of 2x4 blocks, where each block contains an 8x16 arrangement of threads. The second code segment performs the same assignment to the grid and block variables in a more succinct manner. In the first line, constructor functions for the built-in vector types are invoked, assigning the arguments to their respective fields. The kernel launch is the same as in the previous case. Finally, for one-dimensional grids and thread blocks, integers can be used as execution parameter arguments. The previous two slides discussed how the kernels are launched from the host code, in particular how the dimensions and sizes of the grid and blocks are specified in the execution configuration. In the next few slides, we discuss how the device code gains access to this information and how it is typically used. All code that runs on the device, namely functions declared with the global and device function qualifiers, have access to 4 automatically defined variables of type dim3. 2 of these variables, gridDim and blockDim, contain the grid and block dimensions supplied by the host in the 2 arguments of the execution configuration. Recall that all threads run the same kernel code, and in order for the threads to perform independent work, a unique thread ID is used to access different data. This unique thread ID is created from the other 2 automatically defined variables, block IDX and thread IDX. Block IDX contains the block index within a grid. and thread IDX contains the thread index within a block. Unique thread IDs are generated from the built-in variables by mapping the local thread index to a global index, which typically is used in turn to access different array elements. This mapping makes use of 3 of the 4 automatically defined variables: block dim, block IDX, and thread IDX. The one-dimensional example demonstrates how this is done in a grid of 3 blocks with 5 threads per block. The product of the block index times the block dimension provides an offset to the local thread index, and the sum of this offset and local thread index results in a unique thread ID. This is only one way in which a unique thread ID can be created. One can use other mappings as well. This slide shows 2 small kernels, both of which are passed a pointer to an integer array as well as an integer value to be assigned to each element of the array. The first kernel is not a particularly useful kernel in that all the threads executing the kernel assign the value to only the first element of the array. The second kernel represents a more typical situation where a unique thread ID is calculated in the first expression using the automatically defined variables block dim, block IDX, and thread IDX. Here, each thread uses the unique ID to assign the value to different elements of the array. There is an inherent assumption here that the execution configuration has been chosen to launch at most as many threads as there are elements in the array. Having given some examples of kernels, we now look at a CUDA example containing both host and device code and compare it to the traditional CPU implementation. Both the CUDA and CPU codes increment each element of an integer array. In the CPU main code, a function incCPU is called with 2 arguments, a pointer to the array and n, an integer containing the number of array elements. The function incCPU contains a loop which increments each of the n elements of the array. In the CUDA host code, the variable block size, representing the number of threads in a block, is used to initialize dim block and in the following line to determine dim grid, the number of blocks in the grid. The ceiling function is used for the case where n is not evenly divisible by block size. In this case, more threads than array elements will be launched by the execution configuration, since all blocks must contain the same number of threads. The kernel code will be responsible for avoiding out-of-bounds addressing by the extra threads. The incGPU kernel is launched using dim grid and dim block in the execution configuration. The array pointer and array size n are passed as is done in the CPU function call. In the kernel, the first operation performed is the calculation of a unique thread ID for all threads executing the kernel. The kernel then checks to see if the thread ID used as an array index would perform an inbounds memory reference. If so, the array element is incremented. If not, then no operation is performed by that thread. When comparing the CUDA and CPU versions, one should note that the actual code to increment the array is the same. The difference is that the loop in the CPU code does not exist in the CUDA kernel. In essence, the loop body of the CPU code is replaced by many threads executing the CUDA kernel in parallel. The threads are launched by the execution configuration in the host CUDA code. Data movement and kernel launches in host code have different synchronization characteristics. All kernel launches are asynchronous in that control returns to the host code immediately. On the device, the kernel will only begin execution until after all previous CUDA calls have completed. Data transfers via CUDA memcopy are synchronous. Transfers using CUDA memcopy are initiated only after all existing CUDA calls have finished and return only after the data transfer has completed. One can manually block host execution until all previous CUDA calls complete using CUDA thread synchronize. This is useful when using asynchronous memory transfers, which will be discussed in the optimization modules, or when timing kernel executions. Aside from these 2 situations, CUDA thread synchronize is typically not needed due to the synchronous nature of the data transfers via CUDA memcopy. The asynchronous kernel launches allow simultaneous execution of host and device code, as demonstrated in the example on this slide. In this host code segment, data is sent to the device using CUDA memcopy, which returns control to the CPU after the transfer has completed. The kernel is then launched, which returns control to the CPU immediately. In this case, the function run CPU stuff is executed on the CPU, overlapping execution with the INC GPU kernel on the device. After run CPU stuff completes, CUDA memcopy is called. If the kernel has completed, CUDA memcopy will begin transfer of data to the host. Otherwise, CUDA memcopy will block until the kernel has completed. Just as CUDA has function qualifiers for indicating where functions are invoked and where they are executed, CUDA has variable qualifiers used to indicate in which memory space a variable resides. The device variable qualifier can be used to designate that a variable resides in global memory, which is large, has high latency, and is not cached. Memory allocated with CUDA malloc is an example of device memory, is accessible by all threads, and has the lifetime of the application. The shared variable qualifier is used to indicate that memory is to be stored in on-chip shared memory. The amount of shared memory can be specified either at compile time or at kernel launch, and is accessible by all threads in the same thread block. The lifetime of shared memory is that of the thread block. Unqualified variables in device code are placed into registers, space permitting, or are stored in local memory. Local here refers to scope. The data is local to each thread. Physically, local memory is off-chip in DRAM and has a large latency like global memory. Both register and local memory have lifetimes of the thread. We mentioned on the previous slide that shared memory can be specified either at compile time or at kernel launch. In this slide, we demonstrate how this is accomplished. If the size of a shared memory array is known at compile time, then the array is declared to be of that size in the kernel, and the kernel is launched with an execution configuration specifying the grid size and block size. If the size of a shared memory array is not known at compile time, but is determined in the CPU code leading up to the kernel launch, the amount of shared memory can be specified dynamically by a third argument to the execution configuration. In the example on the right, the shared memory space specified is equal to the space required for block size floats. In the kernel, the extern keyword is used along with empty square brackets. Both of these methods can be used simultaneously, so that a kernel can use statically as well as dynamically specified shared memory. We previously discussed host synchronization in respect to data transfers and kernel launches, and how CUDA thread synchronize can be called to block the CPU code until all CUDA calls on the device have completed. The GPU also has a synchronization function, double_sync threads, which is used to synchronize threads within a block. It is a barrier synchronization, meaning that no thread can pass it until all threads in the block reach it. It is needed because the order in which threads of a block execute is unspecified and is used to avoid read after write, write after read, and write after write hazards when different threads access the same address in shared memory. Sync threads is allowed in conditional code, but only if the condition evaluates identically across the entire thread block. For example, in the code at the bottom of the slide, the sync threads call is allowed since the condition is based on the block ID and will therefore evaluate identically across all threads within any block. GPU atomic operations allow different threads to safely modify the same address for associative operations or operations where the order of execution does not impact the result. These operations include add, subtract, increment, decrement, min, and max, logical and, or, and exclusive or, as well as exchange, compare, and swap. Atomic operations are available on certain NVIDIA GPUs depending on the GPU's compute capability. The compute capability is used to keep track of certain features available on GPUs, such as which atomic operations are supported. Atomic operations on 32-bit words in global memory require a device with compute capability 1.1 or higher, such as the G84, G86, or G92. Atomic operations operating on 32-bit words in shared memory and on 64-bit words in global memory require devices with compute capability of 1.2 or higher, such as the 10 series architecture. We have already discussed one specific built-in vector type, DIM3, which is used in the host code to specify the execution configuration and by the automatically defined variables in device code used to calculate a unique thread ID. The programmer has access to other built-in vector types, both from host or device code. These types are derived from basic integer and floating point types and contain from 1 to 4 components, which are accessed by the fields X, Y, Z, and W. None of the example codes given so far have utilized CUDA's error reporting capability. This was largely done for the sake of brevity. Here we discuss how error reporting is used in CUDA. All CUDA calls return an error code of type CUDA error sub t, with the exception of kernel launches, which must be of return type void. It is possible to get the error code for kernel launches using the function CUDA getLastError, which returns the code of the last error. For detecting kernel errors, one should use this after a CUDA thread synchronize call to ensure that the kernel has completed. Once the error code has been obtained, it can be supplied as an argument to the CUDA getError string function, which returns a null-terminated character string describing the error. This finishes the CUDA Programming Basics modules. Only the basic features of the CUDA API have been covered in these modules. For more API functions, see the Programming Guide and check out the Advanced CUDA Programming modules.